Hey, welcome everybody. Welcome to our NCAT webinar series, From Research to Implementation series. This is our November 22, the last one of the year edition. Today, our topic is going to be the cost-effective use of high polymer binder mixtures. We've got some exciting stuff that's gone on there. And so we're going to go ahead and jump into that. Our presenters today is Buzz Powell, as always. And we've got Dave Tim as well from Auburn University and NCAT that does a lot of research with this kind of work. And we've got Howard Mosley from the Florida DOT. A couple of housekeeping things real quick. Please give us your comments in the chat box. I'll remind you there. We'll gather those up at the end. And then we'll try to cover as many of those as we can. We want to try to get through all the presentations, make sure we get you the information. So real quick, let me introduce everybody, and then we'll kick it on from there. So Buzz Powell, he worked for 12 years with the Alabama DOT and then 2 years in the private sector before he joined NCAT as the first test track manager in 1999. And he's now an associate director here at NCAT and an Auburn University research professor. Dr. Dave Tim is the Bradsfield and Gorey professor of the Civil Environmental Engineering Department here at Auburn University, where he also serves as an associate department chair. He's been at Auburn for the last 22 years. He mostly teaches on asphalt pavement structure and design and analysis methods. Much of Dave's research takes place at the NCAT test track, and he's a registered professional engineer in Alabama, and he is a phenomenal solar photographer. That wasn't in his bio, but I'm going to add that in there. Really cool stuff. Then Mr. Howard Mosley, he's worked for the Florida Department of Transportation for 24 years. He currently serves as a state materials engineer there in Gainesville, Florida. He's a licensed professional in Florida. And he's a graduate of University of Florida. He's got his degree in civil engineering and a master's in '99. So given all of that and the chaos that happened behind me, I apologize about that. I'm going to turn the time over to Buzz. He's going to go ahead and talk about the background of the cost-effective use of the high polymer binder mixes. And then he'll hand it to Dave, who will talk about the NCAT research. And then Howie will round us out with some discussion on some agency perspective and things that they've seen there. And Buzz will bring us back and tie it all together, and I'll help us get the questions done, and we'll be on our way. Given that, Buzz, please.
All right. Well, thank you so much, Travis. And I'm really happy to be here with you again this month. And two of my good friends, Dave Tim here at Auburn and Howie Mosley from the Florida DOT. And those of y'all who've done these webinars with us, these monthly webinars in the past, know that we essentially take these through 4 steps. I typically talk a little bit about the background and as it relates to the track, and then we have our subject matter expert here at NCAT and Auburn University. That's Dave for this month. Talk about the research. The practical use is we like to have people from the agencies or people from industry who have experience with implementation of these technologies to really get as much practical information out there as we can. And then I try to bring that together at the end and in takeaways. And we like to say that really this is about, we're not trying to just promote the positives. You know, when it comes to some of these new technologies, we really want to address the good, the bad, and the ugly. And in that way, people know what the benefits can be, but they also kind of know what the concerns need to be and what they're getting into when they decide to tackle the types of innovations that we include in these webinars. So I always start out with the track background for any new attendees that we might have this month. The track has been operational since 2000. We started the project in '98, and I have been associated with it since '99 when we were still doing dirt work and the buildings were shelled out. But the National Center for Asphalt Technology was founded in the mid '80s, essentially to make asphalt roads a better investment. And then the test track we began to pursue that project in the late '90s, essentially so it could be a giant outdoor laboratory with actual legally loaded axles, a whole bunch of them as we pull them in triple trailer trains. And the idea here is, you know, we can do testing and modeling and a lot of high-end research like a lot of organizations can, but the proof is always on the road. So our goal with the test track is to really be a proving ground for state DOTs like where Howie works with the Florida DOT, so that we can help help DOTs to make to implement the right kind of change. That really is what we say that we do here. And it's really all about safe and sustainable asphalt pavements at the lowest possible life cycle cost. So we do a lot of standalone experiments. We do a lot of section comparisons. We do a lot of group experiments. And then we do research in 3 different areas. We do research with mixing materials. What are the ideal combinations of materials to put in the layers of the pavement structure? Then if you have the right combination of materials, how thick does it need to be? And then finally, if you've got the right mix of materials and the right thickness, then what's the best roof on the house, which we refer to as preservation. The neat thing about high polymer binders is we have some of all of that in our discussion of high polymer binders as it relates to the history on the track. So that's kind of my job at the front end of these things, is to describe the history that we've had at the track. And it started in the laboratory back, I think, in 2008 with what we call a phase 1 experiment, but it resulted in a thinner test section in not inside the group experiment, what we call the group experiment, but really the kind of a GE plus test section. So the group experiment, we had 5-inch, 7-inch, and 9-inch pavements, and the Creighton HiMA binder funded test section really was intended to show, hey, we can build these pavements thinner and get thicker pavement performance out of them. That experiment did so well that we had a totally different test section that had a really high PI clay as a subgrade that was not intentionally designed to be not thick enough. So we had a full depth failure in it, and we ended up doing an N7 like mill and inlay salvage to convert a failed structure into a perpetual pavement by focusing on inlaying what we proved would appear to be perpetual in section N7. In 2012, based on those successes, we built what we called at the time the Green Group Experiment. And these group experiments are, multi-state collaborations. And within that experiment, we had a high wrap focused test section that had a 35% wrap base layer with HiMA binder for the purpose of being highly strain tolerant. And that section did really well. Also in 2012 and pushing forward into 2015, we had thin lays that we produced with HiMA binder on Lee Road 159 on US in 2012, and then on US 280 in 2015, and then County State Highway 8 and US 169 up in Minnesota in 2016. All those were with HiMA binders, and then also in 2015 we built what we call the cracking group experiment. That was an experiment set up to essentially determine what laboratory cracking tests relate well to observed performance on the test track. And so that experiment, we had thin pavements that would deflect a lot, but we were studying near surface cracking in the top 1.5 inches. So the bottom of 4.5 inches was produced with HiMA binder to make sure that we would get those deflections that we wanted, but without bottom up fatigue cracking. And we had 7 layers that we built with HiMA binder in that experiment. In 2018, we did approximately 8-inch thick lift paving, single pass, 8 inches compacted thickness in a single pass, that we also built with HiMA binder using warm mix additive in sections N10 and N11. That's because we were studying thin lay performance in N10 and 11. So again, we wanted some deflections, but we wanted to not have any distresses from the underside that would confound the research. And then that turned out very positive. And then finally in 2021, kind of in additive group plus test sections, we're evaluating high polymer alternatives. And the alternatives are being studied in section S8, a product called Sigma Bond, and then in S13, a product called B2 Last. So that is the kind of the track background. So I'm going to stop my share here, Dave, and I'm going to turn over to you so that you can do a deep dive on part of what I just presented.
All right, can you all hear me and see me okay? Buzz?
I'm seeing your screen, yes, sir.
Okay, perfect. Thank you, Buzz, and it's good to be with everybody this morning. Thanks for taking time out of your busy schedules to listen to us talk about high polymer mixes and high polymer binders. As Buzz provided a really good overview, we could really probably host a multi-day conference or symposium on the experience we have using these types of materials at the test track. I'm going to focus on two studies in about the 20 minutes that I have this morning. The two oldest ones that he mentioned, the one in 2009 using the HiMA mix, and then the rehabilitation that we did in 2010 on a badly failing section. There's certainly more information, and if you're interested, we can get you lots of reports and things if you're interested in more details, but I'm just going to focus on those two studies this morning. So when we think about loading up polymer into binders and into mixes, there's certainly some advantages of why we would want to do this. And first and foremost is the potential to improve cracking resistance by having that polymer in there. It'll toughen up the mix and make it more potentially more crack resistant. We can increase the elasticity and with a fixed or lower modulus, and maybe also improve the rutting resistance. So those are some pretty good advantages. In fact, some of the reasons why we use conventional polymer loading around, say 1 to 3% or something in that ballpark, if we get those sort of advantages. But the potential disadvantages, if you start putting too much polymer into the mix or into the binder, is you may have poor compatibility with the binder. You may have some workability issues. It might be difficult to produce it and difficult to place. And so these are some of the downsides. And this is really on this side is really sort of a chemical engineering challenge, is how can you overcome those things to achieve the advantages without the disadvantages. And when we started talking with Kraton Polymers back in, I guess it was about 2008 or so, they had just developed a new formulation that used in the neighborhood of 7 to 8%. What we put on the track was a 7.5% SBS. And they had, through chemical engineering and their knowledge and experience, had overcome some of those disadvantages with workability. And they had done some pretty extensive lab testing that showed that this had a high potential for use in paving, but hadn't yet really built any significant projects with a lot of traffic on them. And notably down here at the bottom is the laboratory studies had indicated they could perhaps reduce the thickness by up to 40%. But as Buzz mentioned, and we believe strongly at the test track, the proof is in the road, and let's build a section and see what happens. And that's how we got involved with them initially back in the 2009 experiment. So just to give you a quick overview of a very stick figure overview of how this works. So at a 2.5, if you have asphalt and about 2.5% polymer, you have the asphalt phase, you have the swollen polymer phase. And if you look at it under a microscope and kind of a micrograph like this, you have the polymers distributed in the continuum of asphalt. And that's true up to about 5% or so. But what happens is when you get up to say a 7.5% or 7 to 8% polymer loading, you go through a phase inversion where the polymer swells and absorbs the asphalt. And so now, instead of having, in the top picture here, instead of having polymer dispersed in asphalt, you now have asphalt dispersed in polymer. It really toughens the mix and really fundamentally changes how the material behaves. Again, there's a lot of chemical engineering that's going on when you do this that I really don't have a very deep understanding of, but that's how it's been explained to me. And what I'm going to focus on is some of the full-scale structural characteristics of these materials. So in 2009, we had the opportunity to work with Kraton to build them a test section. They came to the test track as a full sponsor, as if they were like a state DOT. And they built a test section, section N7. And here's Bob Klutt. Some of you maybe know him, and we're paving their section. And it was part of a larger experiment that we had a number of other group experiment sections going on that were built at 7 inches thick. So what I'll refer to in the upcoming slides as the control section is essentially 7 inches of total asphalt over granular base over subgrade soil. And these have sort of conventional polymer loading or no polymer in one case in the base mix. versus a thinner, I'll just refer to it as HPM, or the high polymer mix, and it was built about 1.25 inches thinner than the control section. So when we start looking at some of the data, remember that N7, the high polymer section, is thinner than the control, and also has all that, that extra polymer in it. Just to give you a quick overview of the comparison, we have the wearing, binder, and base courses, and you can see the thicknesses here and so on. The polymer loading, as I said, in the wearing and binder courses, we did have SBS polymer in the control, 7.5% in the Kraton. No polymer in the base mix for the control section. You can see how it grades out here. The volumetrics were fairly comparable between the two. The plant temperature, we ran it a bit higher for, I think this was on the recommendation of Kraton, was to run the plant a bit hotter when working with that material. And then you can see here the compaction temperature. We do a lot of FWD testing and back calculation at the track, and that's what this plot is showing over the several years worth of testing. And it's interesting that we got very similar modulus, especially, right around, say, about 75 degrees or so, these two lines cross. The yellow is Kraton, the blue is the control. But we see that it's a bit softer at the low temperature and a bit higher. And we see this up from conventional polymer loading as well. But we see kind of a shallower slope, and we're seeing some advantages here that come out in the rutting and cracking performance in the modulus curve here. So comparable, but a different slope that we get from the data. So these sections were in place for 2 test cycles. So we had a total, on the right-hand scale is the easel count. So up here is 20 million easels, the full 2 years. The flat lines of all 3 series, that's the gap between test cycles when we're doing other rehab work on the track. And the left-hand scale is the total rep depth. And so what we would call failure at the track would be a 1/2 inch or 12.5 millimeters. So right here, neither one of these approached a rutting failure point, but you can see improved performance out of the Kraton section coming in again, about 1.25 inches thinner. We had about half the rutting or less than half the rutting from Kraton than we did, or the high polymer mix than we did the control. So very good rutting performance from both of those, which wasn't a surprise when we ran these through the APA and did our rut testing on our specimens. We saw that it had improved rutting performance in this laboratory test. So that wasn't a surprise to us. When we look at cracking, this is interesting. We did see cracking in both of the test sections, but I need to point out that these 2 plots were selected because they look very similar in terms of how much cracking we see. The control, this occurred at 17 million easels is when this got to this point. And the high polymer mix was at 20 million easels. So it outperformed the control, number one. And then number 2 is, and I don't have a picture of it, but the maps that you see, they look similar, but when we did forensic coring and trenching of these sections, all the cracking in the control was confined to the surface. Whereas, all the cracking in the high polymer section was confined to the surface. Whereas when we did the same kind of forensic examination in the control, we had cracks that went all the way through. So this had bottom-up cracking, and the high polymer did not have bottom-up cracking, which again wasn't a surprise. If we look at bending beam fatigue testing from the laboratory, we have a bending strain on the vertical scale, number of cycles on the horizontal scale. It's like an order of magnitude, or maybe 1.5 orders of magnitude greater or better with the high polymer material compared to the control. And then we also did some projections of where the endurance limit is. I'm not going to talk about perpetual pavements today, but we do see if you're using this material in a perpetual pavement scenario, you have a much higher endurance limit, which means you could build a significantly thinner pavement with this material, theoretically. To look at the tensile strain measurements, so we embedded gauges in these test sections during construction. We make measurements over those 2 years. The vertical scale is the bending strain that we measured under truck traffic, and then this is at 3 different reference temperatures. What was really interesting is at the kind of cooler and moderate temperatures, there really was no difference between the 2 sections. And remember that the high polymer section, it was built 1.2 inches thinner. And so we should see it, if everything else was equal, we would see a much higher strain in that section, but the changed properties due to the high polymer loading means that we see very similar, statistically similar strain levels there. And then when we get to the warmest temperature, let's say 110 degrees Fahrenheit, the increased modulus that we determined through back calculation and testing gave us a lower strain level. So all that kind of links together in terms of, you know, our expectations from lab testing and then field performance. I'll switch gears now and talk about the other study that Buzz mentioned, the second one that he mentioned, which was doing some rehabilitation with the high polymer material. And this was actually part of a perpetual pavement experiment, unrelated to what Creighton was wanting to accomplish with their test section. It was just an adjacent section where we were looking at kind of differences in thickness. And this was a section, or these sections were sponsored by the Oklahoma DOT. So the difference here essentially is that we had 10 inches on top of that soil that Buzz mentioned, that poor soil that we imported. We had 10 inches of AC in section N8 and then 14 inches of AC in section N9. And what I'm going to focus on is section N8 because as we were hoping to see, and what Oklahoma DOT was wanting to see, is that we would see failure in N8 and don't see failure in N9. We saw a lot of failure, and in fact got to a point where we had to operate in almost emergency mode to be able to continue putting traffic on the section. So this is looking just at section N8. We had the original construction, and after the first 10 million easels, we saw extensive cracking in the section. And in discussions with the Oklahoma DOT, they asked us to do what they normally would do in this situation, which would be to mill off. And in this case, they asked us to mill off about half the depth and then put back in the same material that we originally had. We'll call that the rehab dense layer, put in a paving fabric, and then SMA on top of it. So essentially rebuild about half the section and add in a paving fabric. This made it about 3.5 million easels before we had a lot of surface distress, and trucks were having to veer around this test section. It started to impact some of the adjacent sections. And that's when I think it was Nam Tran and Buzz and a few others had this idea of, well, we've gotten what we can out of N8. Now we have to hopefully make it last for the next 7.5 million easels to get to the end of the test cycle. Well, let's try putting in this high polymer material on top of an extensively cracked and damaged pavement, and let's see how it performs. We had a lot of confidence coming out of what we were seeing in the adjacent section N7. Let's try it here and see what happens. So we milled out a little bit deeper than what we had originally. So we went down just a little bit deeper and then put in these high polymer mixes. And it was pretty remarkable what we saw in terms of performance. This is rut depth versus easels. So this is the first test cycle to 10 million, and then the second test cycle to 20 million. Just for comparison, the 14-inch section, the perpetual, it did just fine over the 20 million, which we expected. But the non-perpetual, in the first 10 million, we were up at this rutting failure point. We did the conventional mill and inlay to bring it back down. And then in about 3.5 million easels, we're approaching a failure point again. This is where we said, well, we got to do something more aggressive. We did the high polymer mill and inlay, and then it maintained itself in terms of rutting performance through the end of the test cycle. This is section N8 after the first rehab at 3.5 million. So this is the conventional rehab, and you can see water standing in the wheel path from the extensive rutting. You can see other things going on. Whenever we've got cones out on a section, when we're under traffic, you know that it's a pretty severe situation where we don't want trucks traveling through here. Close up of that far end of the section there, the whole mat is kind of shoving off to the side. We're in a very serious situation in terms of being able to get this section to make it to the end of the test cycle. And so again, we did that high polymer mill and inlay. It improved the performance. We were able to make it to the end. As part of the investigation we were doing for Oklahoma, we decided to go ahead and do a life cycle cost analysis and see, you know, we're really weighing perpetual versus non-perpetual, but the high polymer figures into this. And what we found was that to have that extra 4 inches of material at the start of the experiment means that we have an increased cost, of course, and that's just the conventional materials. And then our time and traffic at the test track are very condensed, and we speed things up. And so in this analysis, rather than use the real timeline, we had a projected timeline under normal traffic conditions. When would these things most likely occur? So rather than say 2 years in, we said, well, let's make it like 18 years in, that we would do a conventional mill and inlay. That was what we did at the after 10 million easels in section N8. And then we said, even though we didn't do this, we said in N9, let's pretend like we were going to do resurfacing just because of aging and so on. So all those, the cost elements are real, but the time at which are just projections. The time at which we do them are just projections. And then we had to do again another high polymer mill and inlay here to make it last to the end. And when we go through the cost analysis, you know, we had a 32% increase at the start there. But overall, the perpetual section, you know, comes in cheaper when we look at it on a cost perspective. I also need to mention that had we just continued to do this conventional mill and inlay, we would have had the same effort every 3.5 million easels is what we were projecting. And so it would have been even more costly had we not used a more advanced material to deal with the extensive cracking going on in that section. So some of the key findings, just to summarize, you know, what we found in that first experiment was that the high polymer section had equal or better performance than the control in all measures. The rutting was about half or less than half in both the lab and the field. The cracking performance was much better in the laboratory than the field, but in the field, remember that we built it thinner. And so we were trying to get it to where we would see, you know, maybe equivalent or a little bit better performance. Had they been built the same, we would have likely seen, based on the data, much better performance out of the high polymer section. I think the change in modulus is really important, that the fact that we're getting that bump on the high temperatures and it's a little bit lower on the low temperatures gives us a lot of good advantages in terms of rutting and cracking performance. And we were able to effectively mitigate that severe crack in the other experiment in section N8. Without that, we were really scratching our heads about how we were going to fix this, because the problem was not really the asphalt materials. The problem is that we had built it on such a fragile, soft foundation that we needed something that was going to be able to bend a lot further without breaking. And this high polymer material is what did the trick for us in this situation. And it did prove to be cost effective against conventional treatments because it lasted a lot longer, even though it was on top of a badly distressed pavement. I've got a couple of resources here. Travis, I'm not sure how these get shared out, if we have a recording or whatever, but if you just go to ncat.us, there's a publications link and you can find these reports. And they're numbered, but you can find these reports and other reports about the other studies that have been done using this material at the test track. And so with that, I'm going to stop my share, and I think Howie, you are up.
Yeah, that's correct. Let me get everything going here, and want to thank NCAT for the opportunity to present our experience with the Florida DOT, and then you guys tell me when you can see my screen. Hopefully it pops up here in a minute.
It looks good, Howie.
Awesome, great. So if you've never been to our office at the State Materials office in Gainesville, Florida, that's what it looks like. I don't have a pretty view of the lake. I have a pretty view of that courtyard on the left there. And so in Florida, we call, let me get the slides to advance. We call it high polymer binder. So it was nice to see NCAT calling it high polymer binder, but I changed all my slides to say HiMA, because usually when we're talking about high polymer binder in Florida, everybody else around the country and world knows it as HiMA. So you'll see HiMA throughout my presentation. That's high polymer binder. So we started using it back in 2015. It replaced the grade PG 82-22 in our spec books in July of 2017 after a couple of very successful pilot projects. And so what is in Florida? High polymer binder, it's our premium binder to address severe rutting, bottom-up fatigue cracking, as Dr. Tim talked about earlier, and also raveling in open-graded friction course mixtures. And then more recently, we're also using it to address some reflective cracking where we can't mill out all the cracks. So again, it's used for a lot of different things when we've got some significant distresses we can't deal with. We don't use it a lot. It's about 3 to 5% of the mix placed on our system annually. So again, it is a premium binder. All right, so in Florida, what are the requirements? We only allow SBS or SB polymer only in high polymer binder. We don't allow PPA. We don't allow wrap in high polymer mixers at this time. So again, that was kind of the conventional wisdom we had, was we don't want to dilute the premium binder we're paying for, so let's not allow wrap. And then obviously, how do we assure we're getting high polymer binder? It's the more stringent testing requirements on the RTFO residue that you see on the little table there. Again, it's tested at a higher temperature, and then it's got very strict, strenuous, JNR and also percent recovery requirements. We actually don't spec a percentage of polymer like you saw David talking about. We rely on the NSCR testing to assure we've got the product we want. So just a little bit of research that kind of supported our initial decision not to put the wrap in the HiMA mixes. This is a project done by the University of Florida. If you're interested in reading more about it, I put the title up there at the top. You can Google that title and it'll pull a copy of that report up. So again, the primary focus was wrap usage in general, but one of the aspects of this research project was to look at the effect of putting wrap in a Florida HiMA mix with respect to cracking resistance. And the research showed you would see reduced cracking resistance in our mixes if you put the wrap in with the HiMA binder. So that's why we continue not to do that at this time. With some of the more recent work with binder availability when wrap's used, maybe if you put more binder in, you might get a better result. So again, but that's just what we found with our mixes. So where do we use it? We talked about rutting. So we don't have a big rutting problem in Florida, thank goodness. Only about 0.3% of our system is currently considered deficient with respect to rutting. I'm also going to give you a little secret. That is not a DOT road in the picture. That's a county road, but it's close by the office and it makes a great rutting picture when it's raining. But rutting is a significant safety concern. So where we do have localized issues with rutting, and especially where maybe we've used a PG 76 -22 binder that's polymer modified in the past and we're still getting some rutting, that's where we look to use the HiMA or the high polymer binder. And obviously, as we continue to grow in Florida, traffic volumes and loads are increasing. We're going to continue to look for the right place to use the HiMA binder to address rutting so we don't have unsafe conditions like that road there. Some research with respect to rutting, why we feel so comfortable. You may be familiar with our heavy vehicle simulator program here at the State Materials Office. We have 2 of the heavy vehicle simulators now, and we did some high polymer research in the past. And so we took, an equivalent mix with polymer modified PG 76 -22 binder and put the same mix down with high polymer and saw the rutting resistance was essentially reduced to half, again, under the accelerated loading of the HVS system there. What's also neat is we saw we can make a richer mix by increasing the asphalt content by 0.5%, which would normally kind of give you a little bit of pause with respect to rutting resistance. We really didn't see any increase in the rut depth there. We only saw 1/100 of an inch increase. So again, you get really good rutting resistance with the high polymer binder as we saw here in our research and also with some of the research Dr. Tim pointed out earlier. And again, where would we use it? Places where we've got really heavy and slow loads, like inspection stations. You can see that's an old 76 -22 mix there. We got a lot of rutting at that inspection station. Also, high volume intersections or interchanges. This is the intersection at US 301 and I-10 near Jacksonville. You can see there's multiple truck stops there, a lot of trucks. That's a perfect place where we look to use the high polymer binders, an intersection like that where we want the best possible performance. All right, so the next distress we use high polymer binder to address is bottom up fatigue or alligator cracking. And Dr. Tim talked about that at length in his presentation. Thankfully, like rutting in Florida, we don't have a lot of this distress, but it does pop up from time to time. And again, when you have this problem, it's an expensive repair. You're not just milling off a couple inches and putting mix back. That's not going to get the job done. It even becomes more expensive when you're geometrically constrained by curb or guardrail. Now, you can't just build the pavement up and increase the thickness maybe to help. You've got to go deep and start trading, mix for base or doing something else if you're not thick enough. So again, we found that the high polymer binder gives more structural support. and helps reduce those bottom-up cracks better. So when we do have issues like this, we look to use the high polymer binder to address the issue. And again, we've got research to back it up. There's the title of the research that was done by the University of Nevada, Reno. Dr. Sabali, Dr. Haj did that research. And again, they looked at comparing our conventional mix with a polymer modified PG76-22 binder and taking a comparable HiMA mix and comparing the structural resistance, or basically the structural support between the two mixes. They've got a nice facility out there. And what the research essentially showed was there's about a roughly 20% increase in the structural capacity of the HiMA binder mixes. To put it in layman's terms, in Florida, we give all our mixtures a structural coefficient of 0.44. That's what we do. We're still an AASHTO 93 state. And again, what they determined was, through all their extensive testing, both with respect to bottom-up cracking, rutting, whatever, you could increase that structural coefficient to a 0.54 very conservatively. So again, you get that increased structural support that you're looking for. And then here's some places where we do get bottom-up cracking. A lot of times on bridge approaches at interstates, where the interstate was originally built at about 5 inches thick. Over time, we've built that up. It's 10 inches thick, but you got to tie back down into those bridges. You see a lot of fatigue cracking bottom up right at the bridge approaches. And this is a great place to use high polymer binder to address that. So the next distress we use high polymer binder for is in open graded friction courses where we've got a history of raveling or where there's a lot of repetitive stopping and turning movements. We use a lot of open graded friction course in Florida. In fact, half of the department's lane miles are paved or surfaced with open graded friction course. So we're doing a little around 500,000, maybe a little bit more tons of open graded friction course every year. And we tend to put it in places where most people would cringe, like that picture shows there. That's a signalized intersection at 45 miles an hour at an interstate interchange. But again, the concern there was hydroplaning because we get a lot of heavy rain in Florida. And so the designer chose to use an open graded friction course, and you get the result you would expect, a lot of raveling. So we want the safety. Safety's number one. And so we want to make the open graded friction course more resistant to raveling. And so the research we've done shows that we can get better raveling resistance. So in this case, that was research done by TTI. There's the title of the research project if you want to Google it and get more information. But the objective of the research was basically to determine if the high polymer binder in the OGFC in lieu of the polymer modified 76-22 binder would increase the performance and longevity of our open graded mixes. And so the research did conclude that yes, it does significantly improve the performance to the point where it was more than cost effective to have the increased cost of the HiMA binder in the mix. So some places where we would look to use it is where we see raveling. We don't use it in all our open graded friction course, but places that have a history of raveling or where raveling might be anticipated. Like, so there was a place where we had a big weave movement and a lot of raveling there on that little kind of turnoff lane. Another place there is just, kind of a suburban corridor where you've got a lot of turning movement, high volume of traffic in a curb and gutter situation. So we do have a good amount of experience. We've put HiMA binder on over 55 projects since we started using it back in 2015. And we've placed nearly 1 million tons, over 850,000 tons of HiMA mix have been produced to date in Florida. So I do want to do a couple of case studies. The first case study, and if you've seen past presentations, this is the one we usually talk about, was on US 90 in Midway, Florida. So this was one of the first 2 pilot projects we did with the department. And see if I can get it to point. Hopefully you guys can see my pointer arrow. Basically, we put the HiMA binder in between these 2 truck stops. There was a lot of rutting on the project, and it was actually, I'll go to the next slide. It was an interim project. So we only did it in the westbound travel lanes at the I-10 interchange there on US 90 between 2 truck stops. The district reported they had up to 2 inches of rutting. So they had programmed something that's going to make all the asphalt guys on the call there cringe. They programmed a concrete reconstruction project. So, but they needed to address the rutting in the interim. And so having learned of the high polymer research at NCAT, I believe Greg and the folks that were here at the time decided to try it on this project. Again, I want to emphasize it was an interim maintenance project. So we kind of broke some of the rules. They did a single 2.5-inch lift. Normally we wouldn't do one surface lift that thick, but that was what maintenance wanted to do. And then they put the HiMA binder in it. And to date, it's performed quite well. So what this chart shows is the performance. So the red plot there is the laser profiler rut data before the interim project was done. And you can see, the laser profiler is showing, rutting in excess of 2 inches right there, and then a lot of high rutting in other places. The district engineer out there, he told me at one place they were close to 2.5 inches of rutting with a hand measurement. So again, a lot of rutting, and then they laid the HiMA mix, and you can see the blue plot is after 7 years of or 6 years of traffic, and we had 6 really hot summers too, and you can see that the rutting is significantly reduced throughout the corridor with a single lift of high polymer binder. So you're definitely getting the value there you want. I want to do a second case study, and we really haven't spotlighted this one before. If you've seen Gary Fitz do a presentation, he's talked about it, but this is a reflective cracking study on Nebraska Avenue in Tampa. And so give you a little bit of project details about it. This was paved in 2016, and you had a shallow concrete pavement that was overlaid with asphalt. And so you guys can imagine you're gonna get a lot of reflection cracking at those concrete joints. And so there's only 2 inches of asphalt over the concrete. That's all you could do with the geometric constraints. So the plan was to do high polymer binder or HiMA binder in all 4 travel lanes. But unfortunately, since this was kind of in the early stages, we didn't have enough HiMA binders. So you only got the 2 inside travel lanes paved with the high polymer binder or the HiMA binder. And then the outside 2 travel lanes were paved with our conventional mix at the time, which is a polymer modified PG76-22 mix. So again, you had polymer in every lane, but the inside 2 lanes had the high polymer, the outside 2 lanes had the conventional mix. They did clean and seal the joints and cracks prior to overlaying it, so we did get a little bit of help there. But I want to show you the performance difference. So, and again, if you go out there and look at this project, there's a lot of traffic in all the lanes. I don't have any traffic, studies to show if it's equivalent traffic, but it's an urban area, so you got cars in all 4 lanes, pretty heavy. And so we don't have good data early on, but after we got our automated crack detection vehicles, our LCMSs, we started getting some really good data on this project. So we got those a couple of years ago, and you can see that's when we started getting kind of the automated survey data. So, a couple of years ago, this was the performance, and you can see you're starting to get more cracking in the outside travel lanes, the ones that don't have the HiMA. And then the most recent survey last year, there's a significant difference. And these are the number of transverse cracks. And so you're seeing one lane with almost no transverse cracks with the HiMA, and then the other lane's got about half of what you're seeing in the 2 conventional lanes. Now, if you go to percent cracking on the next slide, went the wrong way. There we go. So total percent cracking, now it's really significantly different. So you're seeing you're around 20 to 25% total cracking in the 2 outside travel lanes with conventional mix, and then you're somewhere around 1 to 2% in the 2 high polymer lanes. And so big difference. You're getting your value there easily. So, and then I want to thank Gary Fitz. He gave me these pictures yesterday for the webinar. And you can see the difference. So in this picture, you're getting some transverse cracking across both lanes. There's the 76, there's the HiMA, but you can see there's, in this picture, a significant difference in the width of the crack. It's a lot less in the HiMA lane. And then in this picture on the right, you can see the crack basically goes away in the HiMA lane. So again, a big difference in performance there between the 2 mixes. You can also see that the texture is looking better in the HiMA mix too, as well, compared to the 76-22 mix. And in the picture I showed earlier, you could see a difference in color, like it was a little richer. So again, we've been really happy with the performance on that project. Well, to kind of wrap it up, I want to talk about some lessons learned, especially if you're just starting to use high polymer binder. Supply may be limited. Again, if your suppliers aren't used to supplying it, you know, and you start putting on multiple projects, you may have a supply issue. So you're going to want to monitor the potential projects during design. You don't want to overspec it until your binder supply has a chance to catch up. And I speak with experience on that, because we experienced that issue as we ramped up once we put it in the standard specs. So you want to monitor that, be careful. You don't want to get in a situation where you can't get the binder to your projects and you cause delays. It is going to be more difficult to produce, especially early on, as the suppliers learn to produce it. They've gotten a lot better and a lot more used to it in Florida, but it does take them longer to make it. Some of them also say it'll take more storage capacity at the yard too. So it's important to have good communication between your contractor, your asphalt producer, and your binder supplier. This isn't the thing where they call Friday and expect to have the binder shipped on Monday. We found that 2 to 3 weeks, especially early on, is kind of the lead-in time you want to give them. Also, it is more expensive, so you don't want to use it everywhere. You want to use it where you're really going to get the value. You don't want to blow your budget. So that's what we're trying to do in Florida, is slowly phase it in. We're really going to get the most value out of using it, especially since it is somewhat limited supply. The other thing is it's going to have finite storage once you get it to the asphalt plant. And so, you know, you don't want to leave it in your tank at the plant for a long period of time. And again, depending on who you talk to, you know, you're looking at probably, you know, 2 to 4 weeks, but that varies. And I recommend you talk with the people that are making it on storage time. So what we've done in our specs is we've made allowances if there's going to be storage issues. For instance, if it's been in your tank for a couple of weeks and now you've got, you know, bad weather coming and you're not going to be able to pave it, and you're going to get concerned. So we've got blend down procedures and also allowances to be used in non-HiMA applications, even with wrap, so that the contractor doesn't have to waste it somewhere. That's the last thing you want. So if you go to our specs, you'll see allowances so the contractor can get rid of it. We don't want to get this stuff, you know, hardened up in a tank. And again, we've not had an issue with that. We've just had some concern, and we've tried to address it, be very proactive so we don't have an issue. With respect to constructability, you don't want to place it in handwork areas. Can it be done? Yes. I'll never forget when Greg and Wayne came back from a project and they watched the contractor place it in a driveway where it had gotten specced on accident. And the contractor did a great job with it. But again, ideally avoid the handwork areas. You know, what we'll do a lot of times in Florida is maybe it's in the main line, but not the turn lanes, or maybe it's just in the outside travel lane where all the traffic is, but not the inside travel lane on a multi-lane road. Again, put it where you need it. Don't put it in handwork areas. Also, you know, early on, we've not looked at the data lately, but early on, surprisingly, we have a percent within limits that has incentives and disincentives. Contractors averaged a bonus on all but one of like the first 10 or so high polymer projects. So they had good success. They were able to get density. So, you know, you can produce it with high quality. Also, the smoothness data has been good. So again, on that first couple of years of projects, the smoothness, the average RI for each of the projects where it was placed, where we measured RI on the high-speed jobs, the RI ranged an average RI of 33 to 47. Again, all in the good to excellent range. So again, you can get it really smooth. So with that, that's all I've got. I really thank you for the opportunity to speak today. And again, I guess we'll move into a question phase.
Well, let's go back to Buzz real quick and let him kind of tie everything together, and then we'll bounce some questions because we've got a few that have come in for you, Howie.
Thank you, Howie. That was great. Can y'all hear me okay, Travis?
Yes, sir. We hear you just fine.
Okay, great. Well, I'm gonna try to pull all this together, and a lot of this is a restatement of things that people have said before. We've got a lot of confidence in this because in the track research program, we've used it in structural and mill and inlay and preservation applications. In structural applications, you can get thicker pavement performance from thinner pavement structures. Howie talked about that 20% higher layer coefficient outcome from the University of Nevada, Reno. That's why that is possible. And if you use it for that purpose, you can avoid jacking bridges. You can maintain curb and gutter. You can do faster rebuilds through thinner structures, that type of thing. So there's a lot of different reasons why it might be advantageous to you from a structural point of view. And he mentioned this, we've also proven that it's useful for solving long-term rutting problems, because this mix does rut less than conventional mixes might rut. And you can achieve better rutting performance with higher binder contents and lower voids, which addresses some part of the questions that have been submitted for Howie. And as Dave mentioned, because of that mill and inlay that we did on that Oklahoma test section, you do have the possibility to salvage a completely failed pavement and even convert it into a perpetual pavement with a simple mill and inlay like we did for Oklahoma. And we've used high performance preservation thin lays to get a better life extending benefit. We've done HiMA binder thin lays, preservation thin lays, as thin as 3/4 of an inch. And we've done them in the southern and the northern test sections and had outstanding results. Howie mentioned this, it's really all about return on investment for the much higher binder cost. And I've got LCA listed in subscript there because, you know, we tend to focus on return on investment from a dollar point of view, but we also have to concern ourselves with the impact that this technology is going to have on LCAs. You know, there is a future coming where we're gonna have to include EPD assessments and LCA assessments as part of our selection process. And like any material that we use, we're going to have to look at the EPD impact of these materials. And what I mean by that is you might prove that, well, I'm going to get X years of additional performance out of this pavement with this material. And from a cost perspective, that makes a lot of sense. But that might not make sense from an LCA perspective if the global warming potential is high enough with some of the rules that are kind of coming out of the system now. There, as Howie mentioned, he did a great job. There are things to account for during production, placement, and compaction, and we have experienced that at the test track. But we continue to use it because it's not a big issue. It's just things that you have to account for. And I always kind of put on my contractor's hat and ask myself, would I be afraid to bid and build jobs with this technology? And the answer to that question is no. I wouldn't hesitate. And then finally, you know, we've proven the HiMA binder, the Kraton HiMA binder on the track is kind of the gold standard, but we are evaluating alternatives. And that's some work that's also being done in several different state DOTs right now in order to really open the door for more competition with the performance that we have proven that we can get from the Kraton HiMA binder. So that was all I had, Travis, and those are all of our email addresses in case someone wants to follow up with questions outside of the web meeting. But I'm going to turn this back over to you, Travis, and I've got your other slides queued up if you need to come back to me on this, depending on where you are.
Yeah, I'd prefer that if you don't mind.
Stay with me or go back to you.
Yeah, let's stay with you if you don't mind. Yeah, it'd be great. So a couple questions that we want to hit here real quick. We can advance beyond that one, Buzz, if you'd like. But so Howie, there's a couple questions that kind of come around the idea of what modifications Florida did to their mix design process to account for the binder. So I think one of them is based around, you know, how do you ask for that binder in your specifications, and the other one was what kind of changes did you make to your voids in the mix to allow for the increased binder that you put in the mix as well?
Okay, so with how we specified, it'll be in the plans. It's covered in the spec. So I showed you the table in the spec. It's denoted high polymer binder in Florida. So that grade has specific requirements for the binder supplier. And then the contractor is going to see the high polymer binder, and he's going to know from specs he can't put wrap in it, and so he's just going to put the high polymer binder. So it's just going to order it. And the way we design our mixes, we still design volumetrically, super pave protocol. We did some research at higher higher binder content, but typically we don't do anything during production. That was just research. So we design the mixes just like we do our conventional mixes, in design of 75 or 100 gyrations, depending on the traffic level, 4% air voids volumetric, and we see minimal, if any, difference when using the high polymer binder with respect to asphalt content. The big difference is there's no wrap in those mixtures. But they're designed the same. There's also a question about density. The density requirements are the same too, as conventional mixes in Florida.
Okay, great. You jumped and got John's question there as well. So then I think we've got a question that I think that's from Kansas as well. There, did you have a sense of what extra you're paying for that high polymer binder in the mix?
It's tough to say. I've learned in 20 plus years of doing this, the contractor's biggest secret is what he actually pays for his binder. And so, but what I gather is, and I'm going to, this is a little long answer, but basically if he's paying, you know, $500 for neat binder unmodified, they tell me it's around 100 to 150 more for the 7622 polymer modified, and then another $300, roughly 250 to 300 for the high polymer. Again, I don't know what prices are right now. I don't know. It changes every week. It's gotten so crazy with supply right now. But
so is that is that 2 to 3 above the 7622, or is that 2 to 300 above? So we're talking 4 to 450 above a standard grade binder.
That's what they tell me. But again, I don't have a lot of confidence in that because they guard that better than anything. What I'll tell you, you know, the first few years, we didn't see a big difference in the actual mix cost. And we don't, you know, we just pay for a ton of mix. And part of that though was, I think, you know, they had high production rates, and that's part of it. So we didn't see the huge jump. In fact, there was one project where the big cost was only about $10 or $15 more for a ton of mix of the high polymer versus the conventional polymer. And it was kind of shocking, but again, it was because the production rate was so good. It was just in like one travel lane with high production rate versus the rest of the job that had lower production rate. So, but you know, material costs based on the data I gave you, it's probably, you know, I don't know, $25, $30 in my calculated material cost. Again, factoring also it doesn't have wrap, but you know, obviously contractors, they're going to bid based on, you know, risk and a lot of other things as well as material costs and production rate. So,
Sure.
I think a lot of things go into that.
Yeah. I saw some interesting things when I was with an agency that were similar to that. I did a statewide study over about 2 years' time and found that the PG 76 minus 22 over a PG 64 minus 22 was only costing us about $1 to $1.50 more a ton on a statewide average over 2 years. But I think, like you're saying, project size probably had a lot to do with that. So Dave and Buzz, did you guys have anything that you guys adjusted in the mix designs when you put the high polymer mixes on the track or even on the preservation stuff, Buzz?
We didn't adjust anything on the preservation. It was just a straight volumetric changeover, like Howie said, is a practice in Florida. On the track, what we have done is the base layers, you know, because what we want on the center structure is insane strain tolerance in that lower layer. And so those have progressed air voids. Can you hear me okay, Travis?
Yeah, it bounced out. You got a little weird there for a minute, but it sounds to me like you guys did a regressed air voids to make that work.
Yeah, for thin lay applications, it's just a straight swap. But when we're doing it on the lower layer of a pavement structure, it's not uncommon for us to regress our air voids.
Yeah. Okay, so I see another comment that came in from my good friend Rhonda Taylor in Florida there. She said if the project's got a decent amount of tonnage, that they're estimating about $200 per ton in Florida for their high polymer mixes there. So Rhonda, thank you for that comment. Here's another one that came in real quick. Let's grab this one. It says, any improvement on the low temperature performance of the high polymer asphalt binders? If so, how much is significant? So Buzz, did we put any of this in Minnesota?
We did use this in preservation applications in Minnesota, and then we also used it as part of the northern cracking group test sections in Minnesota. But what was the point of the question again, Travis?
Is there any improvement on the low temperature performance using the high polymer modified binder?
I don't have data to back that up, but I can tell you that when we've used HiMA, HiMA thin lays up in Minnesota for preservation purposes, it's on top of pavements that have really aggressive thermal cracking. And I'll stick my neck out and say that we've seen a bump in performance from that in those applications, but I can't give you like DCT numbers that could give you a data basis of that assessment. That's just me shooting from the hip.
Sure. That makes sense to me. So it looks like a number just came in from Texas that's calling a really similar price per ton as what Rhonda gave us there. So that's good to know. All right. So I think we don't have any other questions that have trickled in quite yet, and we're up against our time here. I really like to end this on time when we can. I do want to give a plug for our next webinar on our research from research to implementation web series. It's going to be on January 19th. After the first of the year here, we're going to talk about the recalibration of layer coefficients using our modern materials and methods. And we're going to have Dave Tim back with us again on that one. Some exciting stuff that was done there, saved one of the agencies that NCAT worked with millions of dollars a year by readjusting that coefficient there. So we're excited to have him back again next month for that presentation there. I want to thank you all for joining. I want to wish you all a wonderful holiday season. And Buzz, I'll let you sign us off.
Well, thanks very much, Travis. And we appreciate everyone being here. It's great to see a lot of friends online. And I just pray that everybody has a blessed Christmas.
Okay. Sounds good. Take care.
Take care, everybody. Thank you.